Okay, I can see my screen.
Yeah, I can see I
Yeah.
can see your.
Okay. So yeah, hello and good evening. I'm Animesh. With me, we have Arpan, and let's start on this. Um, so before we start with talking about what variational autoencoders are, let me first outline the topics that we are going to cover. So we are going to start with what do we want and what are the other ways of achieving the same task of unsupervised learning. In the second phase, we'll talk about some specific architectures of neural networks. In the third step, we'll see the results that variational autoencoders give us. And in the fourth stage, we'll deal with a little bit of maths. Um, so yeah, let's start off.
Yeah,
So
I'll go.
yeah.
So, so what the idea of variation autoencoders is that we want to model latent variables which represent our data better. So, given our data, we want to find other features Z such that Z models our data, and Z can be like a Gaussian Bernoulli or some kind of distribution. And given all the latent variables which are Z, we want to find the best set of latent variables Z, which helps us generate very similar data to X. So, uh, say in our previous slide there were three blobs. So we want to generate data like the one in the first diagram. In such a case, that we can model this data using just three Gaussians, and uh, our entire feature features can be reduced to just three means and three variances. And with only modeling only six variables, we can actually represent this data well. So here at epoch 0, we start with estimating something like the first in the second diagram, and eventually we find the correct mu and sigma and reach the final sample. Yes.
Right. So what we are saying is that we are the observed variables take a huge array of values. So the values are two different real numbers x comma y, but these two real numbers can have many different values. But we know that there exists a much simpler latent structure underneath. There exists a latent structure of which set do I belong to, and then my position in this set is random. So I want to learn as a part of my neural network these distributions, and I want these distributions to mimic what I have. And okay, so I don't think it'll be so it'll not be six variables. It'll be, I think, 9 or something, because you'll have covariance along x and covariance along y, and if they are axis aligned or something. But yeah,
Yes.
so that's the general idea. So we'll start by looking at latent variable models. So let's start with the architecture of what an autoencoder looks like, and then we'll dial back to what are the other types of latent variable models we can have. So first, I guess we should just try to look at this part. And this part says that given some z, this z is our latent space embedding. So this z can be some one hot vector like 0, 1, 0, and this means that our point belongs to the second Gaussian. And the task of this neural network would be to reconstruct back some output values x and some output value y. And this distribution of x and y should mimic the distribution that we had in the figure given. So this may not be exactly 1. The value in the vector will change a little. So this can go from, say, 1.01, 1.02, and so on. And these x's and y's will randomly change based on that, mimicking the entire distribution. So this is our latent variable, and we want to go from it to the distribution. And this part of the network that we call the decoder network is responsible for that. As we'll see soon once we start entering the mathematics section, that just having a decoder and manually feeding in these values, the one hot encodings, is not sufficient, because it will get really hard to train this part of the decoder network. So we also need this mapping to be invertible. So we want to go from the points x to the latent space embedding. So given the figure, we want to see that some point lies over here, so it's a part of our first Gaussian, or if it lies over here or here, it's a part of our third Gaussian, and if it lies over here, it's a part of our second Gaussian. So going from the value x and reverse sampling to the z is also an important task, and therefore we have another neural network which we call Q over here, parameterized by quantities phi, and it predicts the probability of this latent space embedding given the observed variable x. So it gives the probability of z conditioned on x, and the decoder gives the probability of x conditioned on z. Right. So okay. So what are the other? So we want to put this method in with other methods that we already know about. So one method is autoregressive models. What are autoregressive models? Well, you can take this image and you can randomly output the first pixel, and then based on the first pixel, you can train a sort of RNN or an LSTM, the way we just saw right now, and you can try to guess the second pixel and the third pixel from based on the previous two, and so on. And such a model will be called an autoregressive model. And there are several improvements to these autoregressive models by masking and whatnot, and getting to what we call the transformers of today. But on the whole, these models are not very good at mimicking the distribution of the data very well. Another class of models is called the flow models. What flow models do is essentially they say that I have some random variable z, and this z is uniformly distributed, and I have some random variable x, and this x is has some weird distribution, and I want to find a function f of f goes from x to z. Sorry. So yeah, f goes from x to z, and to find this distribution, if I try to find this distribution using my neural network, whenever my function, like whenever many different z's get mapped to the same x, then the density of x will increase, and whenever very few different z's get mapped to the same x, the density of x will decrease. So we have another way of modeling some sort of a density function of where the points are going to be based on flow networks, like just by modeling a single function. And this serves as sort of an inspiration to variational autoencoders, not directly, but sort of mathematically. And then, yeah, would you like to go ahead, Arpan?
Yes. Then we have variational autoencoders. So variational autoencoders, as we discussed, assume that there is a low-dimensional structure to the observable data we get, and the issue with variation autoencoders is that it does not model high resolution, which means that for example, as we will see later, images generated by the VAEs are blurry kind of, as compared to say GANs. So however, they are good at capturing different modes of the distribution, which means that if there are multiple Gaussians, then it will try to capture all the Gaussians and not stick to generating data in one of them, which is the issue with GANs. So GANs are trained using two models. One is a generator and a discriminator, and the generator will try to generate images and fool the discriminator, which will try to classify it as which set it belongs to, and in this kind of a game between the generator and discriminator, the model learns well. However, again, it is possible that GANs do not capture all the modes of the data and stick to only one of the distributions.
Right, so we'll get into the details of what the modes are very soon. But yeah, the general idea is that there are two new types of networks. GANs are also called implicit networks because the actual data or the actual distribution is not fed to the neural network. All we give it is a fight between two neural networks. One is trying to fool the other network by generating fake images. The other is trying to catch the other network by classifying whether the image is fake or comes from the actual image data set. So these will be called implicit, and our variational autoencoders will be latent, because we are saying that there are very few variables, a small set of variables called z, which define the entire data set x, and we can sample from that. All right, so let's start by talking about, so you have already seen the basic architecture of a variational autoencoder. There are several other improvements to this architecture, and the first of these improvements is going to be that we can train this variational autoencoder adversarially, meaning that we can try to get a GAN sort of architecture over here. So we can try to ensure that the latent space embeddings need to look like they are samples drawn from a Gaussian. Why do we want to do this? We want to do this because, say, for example, you have a photo of a rose. So you have a photo of a rose and you have a photo of a lily, and they are put in some low dimensional space. So, say, for example, one is put over here, the other one is put over here. When you are going to walk on the path between these two, you are not going to generate real life samples. You're not going to generate a new flower by stepping over here. So what we want is that all of the points that we put on our low dimensional space are clustered close to each other, and they are a part of some small Gaussian with, like, they lie in some 2 sigma deviation of the Gaussian. So what we do is, instead of we can add one more layer of structure to our variational autoencoder. We have one neural network which is taking the image and putting it into some lower dimensional latent space embedding, and we have another neural network which is expanding the embedding out back to make this number 4. And what we want to ensure is that the internal latent space is compact and looks like a Gaussian. And for that, we try to put up a discriminator architecture, which we call the discriminator of the Gaussian. And we try to confuse it by putting up samples from the actual Gaussian and putting up samples from the latent space of our vector. And if the z's do not follow a Gaussian distribution, then the loss term is added to the neural network. Another type of neural network is another type of autoencoder is what is called the conditional autoencoder, where we give some additional information to both the encoder and the decoder. Like, we can tell the encoder that the image that you are encoding is the number 3, and the image that you are decoding is also, so the decoder will also get to know that the image is decoding is the number 3. And this helps us add some extra structure to the neural network. And this is just the mathematical form of the architecture described. So this helps in improved learning. And finally, we have another trick, and we'll see these tricks in detail if we get the time in breakout rooms. But the final trick is that these vectors that we sample, the latent space embeddings, these are all sampled from a Gaussian. So, like, you can be at rose, or you can be at lily, or you can be at some place in the middle, and you can try to generate new types of flowers from this. But what will happen is that, since all of these need to be flowers, and all of them, like the entire set of real numbers sampled from a Gaussian, need to correspond to some flower, need to have nice likelihood, the images start appearing blurry. So there are tricks of saying that my weights will be quantized, and I hope in the previous lectures you have seen quantized neural networks. So the idea is somewhat similar, but here the latent space weights are quantized, not the weights of the neural network. The latent space embeddings are quantized, and this helps the variational autoencoder snap to very sharp images. So yeah, let's take a look. Yeah.
So here we have two sets of images, and on either of the set, the left one is the ones generated using a VAE, and the right ones are generated using GANs. So as you can see, the images by the VAE will be slightly blurrier, and GAN images will be a bit sharper. However, you can see that VAE captures different modes of the data well. So in GANs, you will see that every image looks pretty similar, with a man just having a fish in his hand, and the VAEs have different types of generated images, and which means that VAE is able to capture the modes of the data better. So basically, VAE will get punished if it does not capture different modes of the data due to the likelihood loss.
Right. So if, say, for example, a single fish alone without a human, the VAE does not capture this mode if it does not see this sort of image, and this image comes in the training data set, it will get a huge penalty, because we are training using the normal neural network cross entropy loss. So we are taking minus log of p, and if p is almost 0, the probability predicted by the neural network is almost zero, the loss will go to infinity. So the VAE is forced to see all of the modes, and the GAN can just stay in one type of image and try to fool the discriminator using only that or a few different types of image. So next, here we see the latent space embeddings of autoencoders. And autoencoders have really nice latent space embeddings because, first of all, they're an unsupervised technique, and where they work pretty well to separate all of the data. But if you train these networks adversarially, the latent space embeddings look even better, with each of the digits getting their own small segment of the space and not overlapping the way they do in normal variational autoencoders. So finally, I would just like to, as far as the theory segment goes, just like to show this video. Okay, I think I'll have to switch to this. This video is of the latent space embeddings from Big GAN. So let me just save, yeah. So this just shows how if you interpolate, if you go from one image to the other in the hidden space, the latent space, how these images morph into each other, and while they are low-res images. By the way, these are the images from Big GAN, not from a variational autoencoder, but they have very similar latent space embeddings and latent space embedding, and this is the one we found easily. So you can see the images going from one to another, and yeah. Finally, so yeah, we are not just interpolating images, we have all of the images compactly in our latent space, and we are finding new points which also look kind of like images. So I guess we should just skip over the math section for now, and if someone would like to explore as to why these neural networks cannot be trained alone, or would like to explore on the exact mathematics of variational autoencoders, we can talk about that. And this would be the justification of, can we train the encoder and decoder separately, and can we meta learn on these? And that's all that we have on the presentation, and we have 5 different collab notebooks. The first one just shows how one distribution can be mapped into another. The second one shows what the variational lower bound is, and how do we compute the loss for the neural network. So the loss computation is non-trivial, and we can take a look at how variational autoencoders compute loss. And the next 3 neural networks, the next 3 are just implementations of the neural network. The first one is a normal variational autoencoder. The second one is the adversarial autoencoder, where the latent space is regularized against a Gaussian by a discriminator. And the third one is this conditioned autoencoder, where you provided additional inputs to both the discriminator and the generator. So yeah, that's all we have.
Right. So thank you, Arpan and Animesh. So now we have. Can you stop sharing your screen? Okay. So now we have 3 rooms, one for each of the topics we discussed today. So all of you can please join the breakout rooms, and if anyone has trouble joining the rooms, then please write in the chat and we will help you to join. So we have 1 hour, so you can ask all your doubts and questions in the respective breakout rooms. Thank you.
Okay, how to join? Hello. Anyone knows how I can join?
Yeah, was Animesh?
Yeah, I don't see my own name. I see everyone else's name.
I'll put you.
Okay.
There's a join button right next to the name.
Yeah, but I don't have my name. I can make anyone else. I can assign everyone else.
No, right next to the heading, sentimental analysis stereo corresponding, right next to the heading,
Got
there
it.
is a join button.
Got it. Thanks. let's wait for complete assignment, I guess. Arpan, are you here?
Yes. So I hope all of you have the meeting link. Sorry, the collab link, the repo link, and you can open the notebooks and collab and try to run it.
If someone has thoughts on what we should do, like should we go over the math of what, like how do we apply loss and what are the terms in the loss function, or if we should just go through the notebooks and see the implementations, please suggest.
Can we accommodate both?
You can go to the
Yeah,
map. Sure.
Okay, so yeah, let's just take a few minutes, like a minute or two till everyone joins. If there are no pure people, there are 18 people unassigned, then just go ahead. Okay, great.
Meanwhile, can you share the link?
Yeah.
Collab link.
Okay, collab links are at the top of.
I have joined
Yeah.
a bit late.
Yeah, sure. Chat, and I can just paste here, I guess. So here you have all the 5 notebooks in GitHub, and at the top of every notebook on GitHub, you have the link to the collab notebook. So let me restart the OBS virtual camera. Okay, so I think there are going to be 18 people who are not a part of the breakout room.
Can you please explain in the beginning that how, let's say, it is different from the GAN in, let's say, basic sense, which you, I think, explained, but
Right.
can you just browse through that thing?
Yeah, sure. Okay, so so there are 2 types of differences we'll have against GANs, and let me just get a whiteboard session up. So one distinction we'll make is, I guess, on the basis of the actual function that they have. So how can I erase clear canvas? Okay. So the first function that we have is, I guess, loss. So the loss of VAEs is negative log of P of each image. So if the VAE is, so the VAE is going to sample these images. So it has some probability distribution. It has some Z, and it has some nice probability distribution over Z, which looks like a Gaussian. So it is like a multivariate Gaussian. So it's a Gaussian on n variables. Now, what happens after you sample from this Gaussian is that this simple Gaussian is going to get transformed to some output image X. And this image X will have some weird distribution. So it will, like, okay, so I cannot draw a distribution over pixels in 2 dimensions, but it will have some distribution. So it may say that images of fish are more likely. So images of fish alone have 20% chances, and images of man plus fish have 80% chances or 70% chances, and so on. Now, what happens of, say, if the image of a cat has a 0 or 1% chance? If the cat has a 1% chance, and if there is an image of a cat in our photo, like in our data set, then the loss it takes is minus log of 0.01, which is like if you take log base 10, it's like how much? This is minus 2, so it will be plus 2. But if you go with 0.0001, so it will be a big number. This is going to get to be a big number. So if the log likelihood, if the likelihood of some element is very low, you are going to get penalized very heavily for it. So if there are many different modes of your data, many different Gaussians, so you need to say that this Gaussian also has high probability, this Gaussian has some probability, and this Gaussian has some probability. So your latent space, which is just one Gaussian, should match, should flow using the neural network to all these three Gaussians. Whereas what would happen if you start training a GAN? If you train a GAN, the GAN will have the generator neural network and it will have the discriminator neural network, and you are giving some images, like you are giving it some random number and you are giving it these images output from the GAN, and it is getting some real images. So the real images will have some distribution, like there are 70% fishermen and 20% man with, sorry, whatever, fish plus man, and 70% 20% fish alone, and it has, say, real images have 1% cats, and say for example generator learns to give 0% cats. Well, the discriminator only manages to figure out that whenever it is a cat, it's from the real images. So it gets only 1% of the cases as a classification loss. So it is getting a very small classification loss here, whereas it is getting a very big log likelihood loss over here in the variational autoencoders. Therefore, it is okay for the generator to ignore these low probability modes, that there are no images of cats and I'll just not generate cat images. And it can focus on these two modes, the 70% and the 20% modes, instead of having to bother with the low density modes. So this is how you manage to, this is the big advantage of VAEs over GANs. Obviously, the other thing is that GANs are implicit networks, so GANs do not explicitly model probability, whereas VAEs actually have, the latent space of VAE has a mean node and so it has a mean and a variance and several means like mu1, sigma1, mu2, sigma2, and so on. And all of these, you draw a sample from this and then you take your neural network to get the sample X. So you know what is the probability of the sample X, given that you know the probability of drawing this particular sample from the Gaussian. So it is also an explicit model in the latent space, which has a direct conversion to the image space. So it explicitly knows the probabilities, whereas GANs don't. And yeah, GANs you can force to, you can get a nice, VAs also give you a nice latent space embedding. So I hope that is clear, right?
Yeah,
Yes.
so there's one question in the chat about why Gaussians. So, so basically, we want to believe that our data can be easily represented in a very simple manner. So that is the idea behind latent space. So Gaussians being one of the most simple yet expressive distributions is a reason we choose Gaussians, and yeah, I think it's clear.
So yeah, exactly what Arpan said. When Arpan says simple yet expressive, I think the Gaussian is by definition the most expressive of all the distributions. And if you want to Google more about this, you can Google that why is Gaussian the highest entropy distribution with finite variance. So there is a very mathematical explanation for this, which actually I'm not familiar with, but that's the term to Google for if you want to figure out exactly why Gaussian. Other than that, as he said, simple to sample from, simple to read, simple to interpolate. So if you have two elements over here, the third element somewhere over here is going to have a high enough, if these two elements exist, some element in the middle will have a reasonable probability. So interpolations have a reasonable probability. But it's also not true that we always have Gaussians. So we just saw vector quantized VAs which are not Gaussian, which are some 0-1 subsets. And the initial example we saw where we had these three Gaussians over there, in the latent space, we just had one-hot encoding. So typically, we can have a one-hot encoding, which is output by a softmax. We can have a Gaussian. We can have a many-hot encoding, which is just zeros and ones that can be output by a sigmoid. Or we can have a long vector where some are Gaussian, some are one-hot, and some are subsets. And all of them can live together. So it's not true that it's only Gaussians, but yeah, Gaussians are the most expressive of all of them. Right.
I think there are more questions. So one is where I think there's a question before about where do we get the classes and what is the cross entropy loss on?
Right. So I think cross entropy loss we'll get to, we'll derive the loss functions. I think this particular question is best to answer after the loss, right? So it's not exactly a Gaussian mixture model because the output is not a Gaussian. The latent space is a Gaussian. So we have a sort of Gaussian, we have a single Gaussian, not a Gaussian mixture over here. So the latent space is a single multivariate Gaussian, and this multivariate Gaussian is getting sampled from, and we are getting a bunch of different outputs, and these outputs have nothing to do with Gaussians. So these outputs are outputs of photos. So and a Gaussian mixture model can never model a photo. So you can see one thing over here, the first notebook that we have, I think it's time to take a look. The first notebook that we have shows that you can start off with a very simple Gaussian distribution. And if you apply some formulae on it, this very simple distribution, given some complicated formulae, like we are multiplying by some number, adding some number, and then taking the sign of, like multiplying it by the sign of some other number. And I think, where is the point that we started with? OST is the point. No, once. Where is our input point? Oh, Z1 and Z2 are the input points. So Z1 comma Z2 was this distribution, which is just a Gaussian. And when you apply these two formulae on it, this gets converted to a very complicated distribution, which looks like a C. And if you want to keep applying these sorts of Gaussian, like you can keep applying these sorts of functions, these complicated functions, you can start to make images like CVIT. So the formula that we are learning over here, these formulae, these are what form the neural network. And the initial Gaussian is just a simple Gaussian, not a mixture model at all. So it's just a single density sampler, so that we can sample, like we have something nice to sample from, and then we transform it into complicated distributions. Because we don't know how to learn complicated distributions easily. We know how to learn simple distribution sampling, and we know how to convert it into a complicated distribution by learning a complex function, because neural networks approximate complex functions. So that's why we are taking this approach, right? Okay. So yeah, this is a nice notebook that CVIT has. So let's get back to the loss function, I guess.
Right.
Okay. How do I from current slide? So the first thing that we can say is the loss that we have is equal to sum of log of p of xi, sum over I log of p of xi. Is this okay? Why is this the formula? Because we are saying that negative log of pxi is the negative log of the probability is the entropy. So this term, like this is what we typically use as binary cross entropy loss or sparse categorical cross entropy. We sum over all the examples and we say that the negative log of probability of that example happening is your net loss, right? So we know that this should be our loss, but now we can write it out. We can write p of xi as p of x time, p of xi can be written as p of x given z times p of z by using the chain rule. And that's exactly what we do. And this is the inherent, the prior probability of z, and this is the p of x given z is given by our neural network. So that's why we are parameterizing it by theta. And this is the loss function that we have. And this is called the prior sampling loss function, because we are just sampling from some Gaussian prior. So this pz is the Gaussian z. So this is the Gauss, and this is the Gaussian, and this is the neural network. And then we can write it out. So the problem over here is going to be that for this, you have to sum over all the different z's. So you have to sum over all the different z's. But there are an infinite number of z's, and we cannot do this. So the simpler thing to do is what is called importance sampling. So one sec. Before we do importance sampling, let's just do sampling. That instead of sampling over all z, we can just take k different samples of z. So you just try for k random values of z, and you just average out the loss for those k values. And this is sort of what you do in mini batch, right? You just sample a small batch and you average the loss over that batch. So you average the negative log likelihood over that batch.
Why the PZ disappears is
So,
because
am I making sense till now?
yeah.
The initial form still looks like cross entropy. Can we not just that? Right. So this form looks like cross entropy, but very quickly we are going to see that cross entropy is infeasible, obviously, because these z's are not like you cannot loop over all z's, and if you could loop over all z's, yes, you would have a very simple cross entropy loss, and a variational autoencoder would be the same as an encoder. But sadly, we do not have this. And the problem is that if you try to just sample k different values of z, you are going to get, so say for example, there are 100 different modes. The way we saw in the Gaussian, we had 3 different patches. But what if there are 100 different patches? The probability of taking any z and getting the right patch, the right log likelihood, is going to be almost 0. So you are never going to get the right value. Let's take a little bit more of intuition over here. So if there are 10 patches, the training that needs to be done is if the correct z for this patch comes up and your point is in this patch. But what if the k batches that you sample are this and this? The k different z values you sample are for these. So your p theta is going to be constantly 0 of sorts, and so this term is going to evaluate out to 0, and you're going to get a massive loss at the end. So this is not good at all. What we need to do is we need to sample at the right place, and for that we'll get some cost function which is slightly more complicated. So if I hope people are getting this till now. If people are getting this, we can go ahead with the second part of how to improve this normal mini batch to get like how to go from mini batch to variational lower bound. Okay, great. So now you have this mini batch. You have sum over z of p of x given z p z. What we can do is we can multiply and divide by qz. So you see this term qz popping up and down. And now you can regroup the terms. So you can group these 3 terms together, and you can take the qz apart.
Hello,
so
Animesh?
right now we had this expectation in terms of pz, but what we have done by multiplying and dividing and regrouping is that we have the expectation in terms of qz. So we have sum over z of qz into some function, which is the same as expectation of this function where z is drawn from qz. Right? So you take samples of z from qz and you try to compute the expectation of this function where you are dividing by q. So now, if you were supposed to sample, like if the distribution p looked something like this, and you were supposed to sample from these places, if you only wanted to sample from these 3 places, because these are the 3 places which are the most interesting to you and train your neural network the most, these 3 places are you can sample directly from these 3 places, and you can divide by the value of q, and you will get the same expectation as the expectation of the whole thing.
Hello, Animesh.
Just a sec. Okay. Okay, that's wait, why can I not hear you?
Hello.
Should I leave room and come back?
No, who's sharing the screen right now? Somebody is in, the guy who's sharing the screen is in speaker view. Hence, it is jumping to every guy whose microphone is on.
Okay. Yeah, Animesh is sharing the screen, but I don't think he can hear us. Just a second. I'll ask him.
Hello.
Recording in progress.
Variational encoders.
Okay, great. So if it's going to generate images, and those images are going to have a maybe some classification here to say, did you generate? Is this the same image, right? Like, or am I getting it wrong?
Right.
Like,
So uh,
yeah.
yeah, so there is no labels here, as in uh, basically there is no it's completely unsupervised. So uh, what the uh, what the goal is to the idea is that it won't generate the same images again, because we are already sampling from a random distribution. So we consider that the probability of generating the exact same images will be very low, but it should generate images which are very similar.
Thank you. Yeah. So okay, if I understand it correctly,
Hmm.
so there's no labels here, and then when you get generate the image, you're trying to see if this image comes on the same distribution, okay, of the input image that you gave, and that distribution is where you're looking at, because the Z distribution, the Z middle part.
Right. Hmm.
Is only from the training, is only from the input image, right? The output image, like that is where I was getting confused. Okay, but what you said makes sense to me. So you're just you don't have labels, you're just comparing, is the output image in the same cluster in the Z space as the input training image, not
Right.
necessarily the same image.
Right. We generate the latent space, which is the Z, from the images itself, and we try to use that Z now and use another network to generate very similar images.
And does the input and the output space need to be the same as in images to images, or can we go from images to something else?
uh,
I
I Yeah.
think you can go from images to something else as long as you know how to convert. Like, you also know a deterministic transform from image to something else. So an example would be going from molecules to their spectra, or from spectra to their molecules. I think you can do that.
I see. So as long as a deterministic function in between, mapping in between, we should be fine.
Right.
And does it need to be a two-way function?
I I'm not sure about that. I think so. I have only used two-way functions.
Okay.
I'm not sure again.
Would you mind sharing your contact information somewhere? So then maybe.
Sure. It's on. So you can just find me on LinkedIn /animeshsena1309, or you can find me on researchweb.replit.ac.in/. I'll share both of the links after.
Lovely. Thank you.
I have a follow-up question, Arpan, on the last function there. So you
Yeah.
generate an image. You generate an image. Once you generate an image, what is the loss here? How do you calculate this loss?
Right. So once we generate the image, we basically sum over each of the possible latent space. So assuming if we could do that, that's what we would be doing. So we sum over all of the latent space. We take the probability of Z. So as we had seen in that formula, we take the probability of Z multiply with the probability of this image being generated if the latent space was Z. And yeah, so this is the part. So P of Z multiplied by P of xi given Z, parameterized by theta, which is a network. And this sum gives me the probability that this image actually belongs to my generated image now belongs to my original distribution. So once we now our goal is to minimize this, uh, like maximize this probability, uh, and yeah, so that's the loss function. That's what it does.
Okay, but Z is what you don't know, right? How many Z's are there like that you don't know, like to make that sum?
Right, right. We don't know. We again estimate it using a reverse process from the reverse process using a function q, I think, which we'll come to now.
Okay, thank you. Thanks for the explanation.
Yeah, Animesh, I think you got
Yeah. Where did I lose?
uh, yeah, I think let's start from the important sampling part.
Okay. So yeah. Did like you could hear everything, right? Um.
Yeah, we
So,
could, but we were trying to stop.
yeah.
It-
So
Anyways, I'll
yeah.
tell you what. If you
Yeah.
could start from the bit where you were referring to this last section, where you were talking about summation over z of gz versus and the three terms there.
Summation over z of
Yeah, the one
one
in
second.
black,
This. Yeah.
one in the
This one.
middle. Yeah, just above that, right? So
Right.
somewhere there. Yeah. Thank you.
Okay. Thanks. So yeah. So what we had was we were summing over z pz into some function of z. And what we realize is that this is the same as expectation of fz when z is drawn from this probability distribution pz, right? So if the probability of any given value of z is pz and you are trying to compute the expectation of fz over this probability distribution, then this is the formula for the expectation. What we did by multiplying and dividing by qz and rearranging is that we changed the expectation into an expectation in terms of qz. So it is as if z's are being drawn from this probability distribution q, and we are finding the expectation of the function pz by qz into fz. So the intuition for this is that, say for example, the probability distribution was something like this hill, 3 hill sort of thing, and I may want to sample only the peaks of the hills, because I feel that here, like, it's too okay. Let me draw this slightly better. So what I want to do is that the distribution that actually existed was that there is a hill and then there is almost nothing, and then there is another hill and there is nothing, and then there is another hill and then there is nothing, and this is what we call P. And instead what we realize is that, okay, I don't know where these hills end, so I want to sample this part, and then I want to sample this part, and then I want to sample this part. So by doing this, I do something called importance sampling. I only sample small parts of the space, and I believe that the rest of the space is something similar. As long as my Q is reasonably close to P, I have got something similar. And this Q distribution, the red colored distribution, is easy to sample from. I know how to sample from it. And by dividing by this number qz, I have fixed the problem that the distribution I'm sampling from and the distribution that I actually was supposed to sample from are not the same, because all I have done is one multiplication and division, and that does not affect my maths. So this division by qz ensures mathematical correctness. And the new function that I'll sample from q, we don't know what q is yet, but this is going to be our this is how we are going to compute our loss for this neural network. Right? So, oh wait, yeah, Arpan, I can still hear you, right?
Yeah, I can hear you.
So as far as recording goes, I think I'm recording on OBS. I'm not sure about recording on Zoom.
We can't record breakout rooms on Zoom. So Animesh is still recording on OBS, so he'll share
Right.
that.
Hey, one other thing. Is somebody got your speaker view on? Then could you switch to the?
What? Yeah. Speaker view on what?
Yeah, so I think the fix to having only animation on your screen is you can pin it to your by right click.
What? I didn't get it.
Yeah, so when someone else is speaking, your presentation stops for a while. So we need to
Spotlight feature.
So you can pin.
Pin what? I don't know how to do this. Can you tell me the steps if I do need to do something?
Yeah, I don't think there is spotlight feature either in this breakout room, because
I think people can individually just pin Aminesh.
Just as individually, just right click and pin.
Okay.
Yeah. Anyway, continue.
Right. Yeah. So now we have gotten this for.
Anyways,
Yeah,
one thing. Can I suggest everybody mute their mics except for when they want to speak? That would also help.
Right. Yeah. That. Right. So yeah, we have ended up with this formula where we are trying to sample, where we are sampling from a nice distribution QZ, and we will see what QZ is, and we are trying to evaluate the loss is going to be this PZ of Z divided by QZ times, like we don't know what FZ is. We know from our previous expression that we wanted to sample PZ times P theta of Xi given Z. So this is going to be our FZ. So let's see on the next page what we have. So now on the next page, we write FZ expanded out. So we say that the answer, that the loss that we have is sum over I of log of 1 by k sum over all the k examples of pz by pz time divided by q times, this is the f function that we had. So this is p theta of xi given zk. And here we are drawing the z's. These z's are getting drawn from this sample distribution q. So we have some hidden distribution Q, and we are taking the Gaussian probability. This is the Gaussian. This is the neural network probability. And this is the probability, like this is the Q probability of, like this is the correction for drawing from Q instead of drawing from P. So yeah, let's come to this KL term later. So how do we expand it out and write it? To expand it out and write it, we can write it as, what did we have? We had pz by qz times p of x given z. So when you take the log, you can write it as, and there was a negative sign outside. We are writing the log likelihood, but the loss is the minus log likelihood. So when you had the negative sign outside, we are trying to compute the expectation based on q's, based such that z is sampled from q, of log of probability of z given x, right? So pz times px given z, pz, so one sec, pz times p of x given z divided by p of x is equal to p of z given x. This is Bayes rule. So what do we have here? We have here just p of z given x. I don't know where this term of p of x went, but anyways, p of x does not depend on z, so it does not, like, we can take it out as a constant. Oh, sorry. Yeah, I got what I did. I got what I messed up. So we are not going from this formula to this formula. We are back to just writing out the KL divergence. Sorry, the last thing I messed up. No, one sec. Okay, so we are starting afresh, right? So now we'll talk about a new formula called KL divergence. KL divergence between any two distributions, say distribution 1 and distribution 2, is defined as the expectation over the entire distribution. So expectation of log of q by p. So for each point, you want to find the value of q, you want to find the value of p. Whatever is the ratio between them, you want to take their log, and you want to sum it over everything. This is a measure of similarity of two distributions. This is called the KL divergence of the two distributions. And you can write the KL divergence as this form: log of q of z minus log of pz given x, because you are computing, you are computing q at z, and you are also trying to compute z at p at z, but you already know x because the neural network knows x. So anyways, and the next thing you can do is you can expand this conditional distribution out into using the definition of the conditional distribution, that it is the probability of both z and x divided by the probability of x happening. So we have this conditional distribution expanded out into this form, and then all that we do is expand out the logs in this form. So we just take these log a by b is log a minus log b. So we have the fully expanded out form over here. The other expansion that we have done is log of z comma x is written as log pz times log pz plus log p x given z. Right. So we are again expanding it back into the conditional form. So we have expanded this out into the conditional form, and we notice that this entire part is what is called the variational lower bound on the loss. And this is, so we can rearrange the terms to write log p is equal to this entire expression plus the KL divergence. The KL divergence is how close our Q distribution was to our true distribution. So we guessed some random values of Z, and there was some true distribution. We have not successfully mimicked the true distribution, but our log probability of X is this variational lower bound. This is the minimum value of X if our distributions exactly match. If we correctly match the right distribution, we did not know what Z's to sample, but if we got all the right Z's, then it will be decided by this formula. Otherwise, it will be decided by how wrong our distribution is. So this is the overall loss function that we come up with, and this is what is known as the lower bound. And again, I hope I'm still there. And this is fully explained by showing graphs and examples in this second notebook, where they explain the log likelihood derivation for VAs. So they show the derivation of elbow. They show how you can use Jensen's inequality to come up with this formula. And they also show how generally variational lower bounds are decided for functions. So Arpan, I'm still there, right?
Yeah, you're still there.
So, okay. So yeah, this is sort of, yeah. So just one sec. So yeah, is this the entire derivation? So we have derived the loss, we have derived the log px, and now that we have derived the log px, the value of log px, what we wanted to do was we wanted to sum over, we said that our initial value of the loss was sigma log px, right? Our initial value of the loss was sigma over I log pxi. So we have now, like, if you take the negative of this and you sum it over all xi, so we have the formula of the loss, and this, the first term, acts sort of as the reconstruction loss. So this is the amount of error that, so if you had a 4 over here and you got something like a 9 over here, so this is the reconstruction loss, this first term. And the second term, which is the KL divergence, is the regularization term. So this helps in ensuring that the latent space looks like a Gaussian and does not just fly out and everyone gets their own point. Right. Do we know Q? We only know Z given X, right? Right. So we never came at Q. Sorry about that. We know Q not directly, but we say that what should Q be like? Q should be like, so we know that there exists some true Q, and Q should look like P of Z given X. So we are trying to learn inside of Q P of Z given X, and we want to learn a nice function Q which we can sample from. And if you have seen our first slide, then this slide, the other network that we need to sample efficiently and we need to train the whole variational autoencoder is the Q network. This Q network is responsible for giving us efficient sampling, so we cannot train the decoder independently. We have to train the encoder so that we can efficiently sample the latent space and we can get a nice loss for our decoder. So our Q is our neural network, and that is the encoder neural network. And this mimics the Z given X function. And this is using this encoder neural network. Obviously, you can get for any point X the latent space embedding of X, or the distribution thereof. Right? So yeah, that's it. And all of this, I guess, is done in the third lesson, where the CVIT people have made, what do they have? Yeah, so they have shown how like the sampler is written, I guess, somewhere over here. They have output the means and the variances, the log of the variances, and this is the Q network, the definition of the Q network, and there is the definition of the P network. And yeah, the rest is the standard torch, PyTorch stuff, how you train, how you save, how you report the loss for the model. And this is the KL divergence formula and everything that we use as the VA objective function. So all of this is written in code and in formulae for everyone to understand. And obviously, we have this in our presentations, which we'll hopefully share. And finally, if you want to take a look, then Berkeley has a full-fledged explanation of the whole thing. So I think in their lecture 4 on their own homework and on their lecture 4 they have latent variable models fully explained out, and all of the math is done in detail. So yeah, the encoder and decoder are trained at the same time, because otherwise you cannot get a nice loss function. The loss will be intractable because Z is infinitely large. So yeah, that's on the plant stuff.
What would happen in case of the CAEs? I'm a little unclear. Because the conditional autoencoders, the Z will be enriched, right?
I think in the conditional autoencoders, the way I look at it, nothing much happens except for the fact that the conditional autoencoder is sort of a regular autoencoder. So you have input, you have the encoder network, you have the decoder network, and there is some extra information that is sort of force fed into the latent space. So there are few variables which are never changed, and the initial network is, the encoder network is free to incorporate it into the other parts of the latent space if it wants, but a part of the latent space is forced to be those exact values so that we can control it. Does it change the function Q? This part of the latent space it cannot touch. Q cannot change whatever it tries. But the rest of the latent space, I did not get what you thought would happen with if you add in conditional autoencoders. Can you repeat that?
Yeah, no, I'm a little curious about how are they, what are the effects, and what are the effects of encoding them either as a floating point number or as a integer, etc. Basically, the way I understand it, it actually segments the space into subspaces where the conditioning variable is actually leading it to a certain part of the subspace, picking the subspace, so to say, the selection variable, right?
Right. I think, I've never thought of it that way, but yeah, I agree with the idea.
But yeah, so how do we? What are the ways? Can we encode a floating point as a conditioning variable?
Right. So I think you can encode a floating point conditioning variable. I do not have a lot of experience with these, but what I know is that people have done this, that they have input, like the conditioning variable has been the spectra of some molecule, and the thing that has been passed is the actual nodes and the names of the atoms and the formal charges of the molecule. So the conditioning variable can be a large floating point vector, or you can have the conditioning variable as a full-fledged graph, and the only thing that you are encoding and decoding is the what nodes are what atom. Like you have carbon, whatever, and you have hydrogen over here. So you can only encode the nodes in a very low dimensional space, and you can pass the graph unedited. So you can have anything that you want on the conditioning, be it a graph, be it a floating point vector, be it an integer vector, anything.
And, anyways, while you were there, what reference are you talking about here? If you just quickly remember the author or the title.
No. So I don't think this is a formal reference yet. This is some partially successful / failed research at CCNSB. So this is attempts that people are making, but I don't know if I mean I've heard this from friends, so I don't know if their attempt succeeded and where they are taking their inspiration from.
I see. So basically, what I hear is that the conditioning variable could be either a regression variable, a regression input, or it could also be a structural input like a graph, right? Okay. Thank you.
Yeah, sure.
Animesh, practically, how do we decide when to use VAE, when to use flow-based models, and when to use GANs?
As far as I know, flow-based are used only when you have to do purely density estimation tasks. So, honestly speaking, the correct answer is just to try all of them, and literature surveys will usually tell you which are working. So, in high energy physics, when you have these particle density estimations, like if you have properties and the particles are very close by and you are trying to estimate densities in very high dimensional space, then you use autoregressive networks and masked autoregressive flows. And when you are using anything in computer vision, or all of the image generation tasks and whatever speech generation tasks, all of them are done by VAs and GANs. I don't think flows and these things are used anymore, because even before autoencoders came, there were wake sleep models. So flows have been out of business for quite some time, other than for purely physics related tasks. I have not seen them used otherwise. So yeah, VAs and GANs are the ones to go with, and people try both alternatingly, and every year there is an achievement in the other one. So people stopped using VAs in favor of GANs, and then this paper called Vector Quantized VAs got published in 2017, and then people started using VAs again, and then the GAN people made improvements. Big GAN came, and other GAN papers came in 2018 or something, and then yeah, the thing keeps on going back and forth. So I don't think there is a clear way to decide. But yeah, density estimators flows for sure.
Sure, thank you.
Right.
So it looks like for waveforms, VAs give a better performance.
Maybe,
you mentioned audio, right? So that's a waveform data.
Yeah.
Right?
So GANs and VAs are both used for audio. I am not sure what is performing how well. So I'm actually not familiar with either CV research or linguistics research. I am in the science department, so.
Sure.
Yeah. That's.
I'm just curious. Would it be? Can you just switch to the VA slide, please?
VA slide at the top. Over here.
This one here. Yeah. So I'm just thinking, is it possible to condition it here in the center?
So you would just say that I will add a new vector over here, a new vector over here. I will concatenate this vector over here, and I'll concatenate this vector with Z itself, and this will get fed over here. Yeah, I think this is possible, right? You can just concatenate and make this work.
Right. So the size of the input and the output network will be different, right?
Yeah. But they're anyways the output size of the input network does not need to match the input size of the output network. Otherwise, these two sizes needed to match. So this output size and this input size is needed to match, but now it no longer needs to match.
Right. Usually, which one is more complex? The encoder or the decoder? What side usually ends up being more complex?
Right. I think the decoder has. So in units we see that they are almost equally complicated. Variational units are made. I am not really sure of which is more complicated, but I think upsampling is the harder task because you have less data and you are trying to generate more data. So I think at least in convolutional neural networks, I see that there are more conv transpose layers put together than there are conv layers. I think it's on a task-to-task basis. I know for units for sure that there are in most Kaggle contests I've seen that there are 2 convolution layers on the encoding branch and 3 conv transpose layers on the decoding branch, but I'm not really sure if that's a generic idea or specific to that network.
Well, I'm not sure if there are other questions from other participants, but if we have some time, Animesh, I'm curious. You mentioned about science. So, do you? Oh, sorry. What did somebody want to say something?
Other messages. Okay, one sec. So you mentioned transformers, extension of VA. No, I am not saying extension of VA. So I'll just try to answer that. The transformers were an extension of autoregressive models. So one idea over here was autoregressive models by sampling one by one each of the pixels was getting very hard. So if you have 1 megapixel image, you will try to sample your neural network 10 to the power 6 times. So there were models like MADE, which said that, okay, what you want to do is you want to make layers, and these layers should connect like this. So the first neuron should give information to all the neurons below it. So each of the layers will look like this. And the first neuron will convey information to everyone below it. And the second one will convey to everyone below it. And the third one to everyone below it, and so on. So the input will go over here and the output will go over here. And this input-output correlation. So this first output neuron will never know anything about what the input is. So sort of you are trying to train each of the future. So you are trying to train this second neuron the second output pixel based on what the first output pixel is, and you're trying to train the third output pixel based on what the first and the second input pixels are. So you are taking the same image as input and output, and you are trying to train it to predict the next pixel given the previous pixels, and then you will try to just put in some random information and try to get out new images from it. So this idea was called masking, and the model was, I think, called MADE. I'm not sure what it stands for, and there was some Berkeley research on it. Again, it's in the lectures over here, so you can take a look at autoregressive models. And this idea of masking, token masking and others have been used in transformers like BERT, where they try to mask a part of the sentence and ask predictions based on it. And masking was again used back in this MADE type models for trying to figure out like the next part of the pixel network, what would be the value of the next pixel. And I think that did well, but still not as good as variational autoencoders. So that's other class of generative models altogether. So I think that's the only question we have, right? Can VAs be used to do pre-training? I think so. You can rotate, like you can try to forcefully encode the different rotations of different rotations of an image and stuff in the encoder and decoder. I don't know exactly how people do pre-training, but I know that some meta-learning ideas can be applied to.
Right.
Yeah.
Yeah. So I have one particular problem where so normally when you use pre-trained resident model, let's say that is mostly trained on ImageNet classification task, right? And then you can use and fine-tune the lower layer if you are doing classification kind of task. But I have a particular problem where let's say you have an image of a document, and there are some kind of symbol, and I need to recognize where that symbol is. So this is an object recognition kind of problem then, right? Right. So in that case, if I take ImageNet pre-trained thing directly, it might not work because so I think Dino or something now do this kind of self-training where you can those kind of model where you can directly use those things for recognizing or localizing the objects also. So is there something of that sort is there?
Okay, so as far as localizing goes, I think we use units are also, they're not variational autoencoders because you are not trying to create new data, but you are just asking about autoencoder training, right? Because you want to localize something. So you don't want to sample from it.
Right.
Right. So autoencoders obviously can be pre-trained. Units obviously have one branch. They have an encoder branch and a decoder branch. So the encoder branch is usually a pre-trained convolution net like, what do we have it? One sec. Kaggle.com/ one sec, I'll just see it on Teams. So you have typically an encoder branch, which is a standard NFNet or something like that, and the decoder branch is a FPN feature pyramid network or something of that form. Let me just see what. Oh wait, we had written the decoder branch ourselves, but the encoder branch was. I'll just take a look over here, and I have posted a link somewhere here of how that works. So we have this notebook. And this notebook used, so the image localization task was done with a two model pair. And where do we have the models? Okay, I cannot find the model definition exactly, but somewhere over here, I'll just link this. This is the implementation of a pre-trained unit with a EfficientNet backbone. I think it's EfficientNet B5 as the auto-encoding backbone. Okay. You can take a look.
Thanks.
Sure, thanks. Any other questions? And if not, we can get back to the science. What are you doing at inference? Do you give a give a Z distribution and let the image generate an image. How do you save Z distributions for each class? Is this in the context of why would I save it for each class? Like my entire Z is from a single Gaussian, right? Irrespective of what class it belongs to. Like I don't actually know what classes are because I do not have tag data. So like my class definition is random, but I have single Gaussian. I sample any point from it. I feed it as this is a multivariate Gaussian. So each point is a vector, and each vector is fed into my neural network, which will output an image. And I trust that my neural network will transform this Gaussian distribution into the true distribution over images. Okay. For multimodal distributions, what latent space representations are good? We don't know, I guess. Like the representation is a neural network. If you are you asking what architectures are good, or just as in latent space will be you are going from a Gaussian to something else. So I don't think you change the Gaussian itself. So the latent space representation stays. Usually it's Gaussian. There is this vector quantized idea that was presented for, again, it's always multimodal distribution. So 2-3 modalities are very low modalities actually. So I'm not sure what happens, but I guess again my general approach is to try out everything, like just try out all the models, run through them and see which one works. I don't know, like I don't have very good intuition on network selection and architecture selection. Right. Anything else?
If there are no more questions, then I'd like to get back to the science question.
Yeah.
I'm curious about what you do and typically the kind of science applications that are on right now.
Right. So what I do is, one sec. Right. So this is one problem of qubit routing. So I am trying to do some like general reinforcement learning tasks in routing. So there are like circuit routing problems where in quantum computers you need to route the closest. You need to put qubits close to each other so that they can interact with each other. And then moving qubits around is very costly and it makes circuits fail. So one of our this was the starter project that we had, and I was kind of new to the field, so this didn't work very well, and it took like 4 hours. Like other people were competing at a few minutes of time, and we took 4 hours to beat the SOTA, which was like at that point in time we were happy about doing better than the state of the art. But then we realized obviously that we are taking way more time and way more compute resources, so it's not that much better than the state of the art. So one thing that we did was circuit routing, and the other thing that I'm trying to do right now is again plotting for quantum machine. Like there is an equivalence between quantum machine learning and machine learning, and I'm just working on trying to plot all of the loss landscapes and trying to plot all of the like if you try to do molecular orbital mapping, if you want to see molecules on weights and biases. So these days I'm just mostly doing both plotting on the end of machine learning and plotting on the end of, so I'm trying to contribute to circ and plotting on the end of quantum software frameworks. So I'm like involved in the software development part of it. Currently, I'm not on any big research project. We just have plotting tasks left before we can start embarking on another, like before we see anything in the space.
Hey, very exciting work. I'll probably take a little time to look up the links you just mentioned. Are you part of a large group in IIIT, or you're just among the few who do it there?
So I think we are now in our lab. We are just 3 or 4 people, and outside the lab we have a senior called Tanuj Khattar, who is a part of Google Quantum AI. So he has been helping a lot with our contributions and helping us contribute to Google's Circ project. So yeah, that I'm trying to work on. So there we have a large community, and now IIIT is funding a new quantum science technology center. I think that will be like there will be a lot more people coming up now. Till now there were not that many.
Yep. How do you spell Google Circ?
CIRQ.
CIRC?
Q. It ends with a Q. Yeah.
I see. let me see if there's a Twitter handle I can follow on that. Yeah,
Right,
thanks.
sure.
Can you just go back to the
Yeah.
top? If I may just look at the title again.
Yeah.
Animesh, I have a doubt. Have you recorded this for the variational autoencoders that you are taking now? This breakout room.
So I have recorded the whole thing on OBS. I'm not sure if it got recorded because it's my first time recording, but I think it did. So I have the recording button here. I'll
Put it
let
in
you
the
know
Discord
once.
channel. If it would be helpful because I was
Sure.
as stereo images breakout room.
What?
I was attending stereo images breakout room.
Right.
This one, it would be helpful.
Right, sure. I'll try. If the recording has worked, I'll surely share it.
Okay.
No, I look forward to that. It was pretty dense and very, yeah,
Right.
it'll take some time. Thanks, Anime.
Right.
Lovely.
Thanks a lot.
Now I think I can approach the maths a little more easily.
Awesome.
Thanks again.
Awesome. Thanks a lot. Yeah. Great then.
No, it was really great session. Thank you so much, Animesh.
Thank you.
Just one more thing. Can we connect with you somewhere like
Sure.
Twitter handle or something? So that would be great because I have some similar interests and it would be very helpful.
I am yet to get on. I am on Twitter. I think my handle is Animesh Sinha 13. So at Animesh Sinha 13, and I am not yet active, or I am on LinkedIn, Discord, everywhere. So if wait, what should I do? I mean, yeah, let's just we can always use Twitter. You can always Google me up like Animesh Sinha Triple IT Hyderabad should result in the LinkedIn page, or what, like, yeah, I don't know.
Yeah, that's cool. Thank you.
Yeah, this is not working. So yeah, thanks a lot. See you everyone, I guess. Everyone should be on Twitter, right? I have a hard time understanding Twitter. As in,
yeah, we'll learn.
Right. Awesome.
Animesh, what is your Discord name? Discord username?
I think it's Animesh Sinha 1309 #5514.
Okay. So is it possible to contact you on Discord?
Yeah.
Yeah.
Okay. I think it would be easiest if you give the email, so anyone requiring.
Email will also be helpful.
Right.
Email would be good. Why don't you type it here?
So Animesh Sinha at research.tripleit.ac.in or Animesh Sinha 1309.
Yeah. Okay. Thank you.
Thanks a lot then. Thanks a lot. Bye bye.
Bye. Thank you.
Bye. Thanks a lot.